Okay, so lecture 29. So this is, our first lecture on the multiple integral. Okay, before going to the idea of the multiple integral, can you tell me how you integrate the function when your function was in, when your function is in one variable? What is the theory behind that? How you do it? Can anybody tell?
So calculate the area under the graph of the function.
Area under the curve.
Yes. So what is that area under the curve?
So basically upper limit minus the lower limit of the curve. Like we can calculate it.
No, I mean, then you are wrong in saying this. This is your x is equal to a, and this is your x is equal to b. Okay.
But
So
it's wrong. It's wrong, sir.
yes. So can you tell me how to calculate the area?
So,
So what's the theory?
Divide it
so
into
basically we can take a
Sir,
small part.
yes, sir. We take a small part of that graph, and then
Yes. Somebody was saying that we divide into, and then you interrupted all. Yes.
so we divide it into small areas so that every part will be covered.
Small areas,
The
No,
small
small
strips
sections.
types.
Small
Small
elements.
rectangles,
Strips.
elements,
Small
small
strips.
rectangles, small intervals.
small intervals. Okay. So let's say these are the small intervals, right? Okay. So these are those small intervals. Let's say this is x naught. Let's say anything. This is say xk. This is xk plus 1. This is xk plus 2. And this is xk plus 3. So these are small intervals actually. And these are what? Rectangles, right? We can compute those rectangle area of those rectangles by taking the lower rectangles or the upper rectangles. So now if you say this, these are the lower rectangles, right? So if you talk about lower rectangles, that means you will get those areas over here, right? So every time you calculate those areas, what do you get? You get that your areas are actually smaller than the required area, right? Is it fine?
Yes, sir.
You're
Yes,
with
sir.
me? But what happens if you increase those rectangles by putting more number of rectangles by, let's say this thing, and then this thing, and then this thing, right? Now, if you get those lower rectangles, so you will come to know that you are getting now more area than the previous case. Okay. So now you're getting this much of area. Okay. And the area which you are sacrificing is actually the area which is somewhere here. Okay. This is the area which you are not getting right now. Fine. Are you with me on this?
Yes.
Yes. But you know that as you increase the number of rectangles, you will get more area and you will come close to the area under the given curve, right? So now there are one more way is also, that is what computing the upper rectangles, and that's what, let's say this, let's say this, and then this, and then this, right? So by computing upper rectangles, you will be getting this. This is the rectangle and this is the rectangle. That means you will always construct the upper rectangle. You will always take the more height, right? So now when you get those areas, what you get, you will get the whole area. That means you will get extra area, which is not the part of the area under the curve if you compute in this way, right? Are you with me?
Yes, sir.
Yes, sir.
Right. So what happens? So in this case, you get extra area, right? And in this case, this is what? This is a kind of underestimation, and this is what the overestimation. So this is underestimation, right? So, but what happens again if you increase the number of rectangles, even in this case? So let's say this one, this one, and then this one, and let's say this one too. So now if you again construct the upper rectangles, you will come to know that now you are closer to the area under the curve, right? So this time, this area, if you see, this area is left out, right? So we have successfully discarded this area. Is it fine? Is it okay? So what happens if you increase, if we increase the number of rectangles, the if you increase the number of rectangles, no matters, upper areas will go down and lower area will go up. Is it fine? Yes. Are you getting my voice?
Yes, sir.
Okay.
Yes.
So is it okay?
Sir.
So basically we come up with the idea that, so this is something like that you take summation and you take hi into f of xi. That means you take the length, I mean, you take the width of that rectangle and call it as h, because you divide it into the equal subintervals. And here you call it the height at x, let's say f of xi. Okay. So your I runs from 1 to n, right? So, but if you take that limit n tends to infinity, right? And let's say you start from here, let's say you start from 0 to xn, I mean, a to b. So that means it becomes your integral, right? Are you with me on this?
Yes, sir.
Yes, sir.
Tell me,
Yes, sir.
are you with me? Okay. So now what about the, let's say now talk about the geometrical interpretation of the multiple integral, that in multiple integral, how that area, that will turn out to be volume rather than saying the area. Okay. So let's move into the pictures and then you will come to know. So let's say you have a function which is of two variable f, x, y, right? So then its graph will be what?
3.
3.
Yes.
3,
तो डोमेन में कितना होगा?
2.
2. ठीक है. So how we plot it? You know that how we plot it? This, and this, right? That's how we do.
Yes,
So
sir.
this is your x, this is your y, and this is your z, right? And then you sort of have a sheet or maybe something else. So let's draw a sheet over there. Okay. So now if you want to, you want to perform a same kind of thing. So here you divide your domain into sub-intervals, small sub-intervals, right? And here you have a 2D domain. So in 2D domain, you will divide your domain into small rectangles, right? So how we do it? So in this way. So let's say you want to find out the area from, I mean, you want to take the restrictions from x is equal to a and y is equal to b, right? So this is your x is equal to a and this is your y is equal to b. So in the same way, here we used to have one dimension. That's why we used to take x is equal to a to x is equal to b. And here we are talking about x is equal to a to y is equal to b. And there may be some more boundaries as well, but I'm taking a simple case. Okay. So what we do, we simply divide this rectangle into the small, sorry. So we divide this rectangle into the small rectangles. This, and here this, and somehow we have achieved this thing, right? So now we want to take the height. So at this point, let's say we take the height. So this becomes the height, this one. So let's say if this point is your xi, yi. So let me write it more clearly. So this point is your xi, yi. So at this point, you get that height, and that is what? F of xi, yi. Right? So in the previous case, I was multiplying hi by fxi. Now I'll be multiplying area of this rectangle. Can you see this rectangle? Let me mark with a
Yes, sir.
different color. This rectangle. Can you see this?
Yes, sir.
Yes. So let's say, we are dividing that subintervals into, let's say we are dividing in a way that each subrectangle has a width of delta xi and length as delta yi. So what is the area of that rectangle then? Delta xi into delta y. So I'll be multiplying with the height. That means f of xi yi, right? So what it will give you? So it will give you a kind of volume. Volume of what? Kind of this pillar. Yes?
Yes.
Is it okay? So if we keep on doing like that, so that means we'll keep on standing the pillars and then we'll finding those heights over there. So what will happen? Yes, can anybody tell me? What will happen? Let's say
So
if I put this.
volume under the curve.
Yes. So I'll keep on increasing, I'll keep on refining that rectangle so that the smaller rectangle will give us a better estimation. Okay? Yeah, you are with me?
Yes, sir.
Yes, sir.
So for each rectangle, we'll finding those heights and then we'll be calculating the areas. So that volume would be what? So how it look like? So it will look like summation n runs from k runs from, let's say k runs from 1 to n into the area of each rectangle, and we know that area of any rectangle is delta xi and delta yi. So let's say for we use a smaller notation over here and we call it as ai. So ai denotes the area of each rectangle. So that means, so how volume will get calculated? Ai times the height, and that would be nothing but f of xi y, right? So that is what? That is something we call it as a volume, right? So let's say we call it as vn. Now similarly, if you take n tends to infinity, so if it makes sense, then it will become what? It will become double integral, and we'll write it as, by using double integral fxy over dA, and this dA is written as dx dy, right? As we have learned that delta x delta y. See, in practice we'll be, most of the time we'll be using dx dy, right? Now you see that in one integral we are doing one integral over an interval, right? Because we have only one dimension, so that's why we are moving from a to b. But here we have a complete region, 2D region, right? So we'll say that over r, over some region r. So that r will keep on changing from problem to problem, and I'll discuss that how it works. Okay? So is it okay? Yes.
दोबारा बताना.
मैंने ये बोला है डबल इंटीग्रल का, मैं ये बोल रहा हूँ कि जिस तरह से हमने यहाँ पे ये लिया ना एरिया, तो उसी तरह से एरिया को हाइट के साथ अगर मल्टीप्लाई कर देंगे तो वॉल्यूम बन जाएगा. और अगर हम n को इनफाइनाइट ले लें, दैट मीन्स ये हम छोटे छोटे बना दें, इनको और छोटा ऐसे ऐसे और छोटा कर दें, तो और छोटे छोटे हमारे पास पिलर्स बन जाएंगे. वो सारा फिर क्या बन जाएगा? वॉल्यूम अंडर दी कर्व z, राइट?
Yes, sir.
Yes. Are you with me?
Yes,
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 sir.
sir.
Yes, you are getting the point. So this is just an interpretation, graphical interpretation, that how we are doing the things. Otherwise, questions are pretty much easy. So these are double integrals are nothing but the volume. Okay. So as we have interpreted right now, so what should I say? Note. Integrals. Of course, we are talking about the definite integrals. Definite integrals in 1D domain in one variable ऐसा बोल देते हैं are areas and integrals in two variables are what? Yes, tell me. Are what?
Volumes.
Volume, right? Volumes, volume, whatever. So is it okay? So it has also some kind of nice properties which are analogous to one dimensional. So few properties. So what are those? So these are, so if you multiply k times, so you can take that k outside, right? So you can take that k outside. This is something which we used to do in the 1D as well.
Yes, sir.
Yes. So that constant can be taken outside. Secondly, if you are adding or subtracting two functions, okay, then you can separate those integrals and you distribute those things over addition, right? Yes. Again, the thing which we used to do in the 1D, one dimensional variable. Yes. Is it fine?
Yes, sir.
So third property, these properties are pretty much similar. We have already done that they are just analogous to this. So if this is greater than 0, then this is greater than 0 if your function is greater than 0 on region R, right? Secondly, so this integral is greater than equal to some other integral, let's say g, if your f of xy is greater than g of xy on R, right? Yes. Is it fine?
Yes.
And
Yes,
further,
sir.
now you know that fifth property is a bit tricky. Let me explain you first. So you know that when you used to do that AB fx dx, you could have, I mean, you are able to do it like this for any C which is lying between A and B, right?
Yes, sir.
Yes, sir.
Right? Yes.
Yes, sir.
But in the present case, how we write it? We write it as your R f of xy. Sorry, your R dA can be written as R1 and plus R2. So can you imagine R1 and R2 over here? Yes. Can anyone? See, R1 and R2 are regions, right? But here C was a number. So C used to satisfy an inequality that C should lie between A and B. But here you cannot say that R should lie between R1 and R2. You cannot say this. So here the property will get converted and your R is something like that. This is your R1 union R2. and R1 intersection R2 is, sort of empty. So what I'm trying to say is, see, let's you have this thing, right? So you have this function and you have this domain. So it's not like that you have to completely evaluate on this R. You can break it like this, right? And you say this is your R1 and this is your R2. Okay? Yes, anybody?
So they are complements of each other.
No, they are actually, we need to make the complete R. So your R is nothing but the union of R1 and R2, right? So you can separate your integral into the, into two parts in a way that R should be the union of R1 and R2, and R1 intersection R2 needs to be empty. Okay?
Yes, sir.
So you can evaluate your plus over here. Yeah. You're with me?
Yes, sir.
Yes. Is it fine?
Yes, sir.
Okay. So let's do a few questions. I mean, we can start few questions first.
Sir,
Yes.
sir, switch to the second properties for just a second, please.
Yes.
Done, sir.
Okay. Okay. So yeah, you got the point?
Yes, sir.
Okay. Okay. So let's, we can try to do few questions on that. Okay. So now there are actually two kinds of boundaries. So two kinds of rectangular regions. So we'll discuss those rectangular regions, that, how these rectangular regions matter. There are largely, we'll be dividing those regions into the two parts. One is rectangular region, another is non-rectangular region, right? So let's say, let's try to find out first of all over the rectangular region. Let's try to do some question. They are very much easy. They are very much nice to us, and we can do few questions on that. So exercise 13.1. Okay, so let's say this is your question number 1, and zero to 3, 0 to 2, 4 minus y square for dy dx. Is it okay? Are you with me on this?
Yes, sir.
Yes,
So
sir.
how you interpret that this is a rectangular region? Can anybody tell me? See, this is your dy. Okay. So these are the limits of y, right? And this is your dx. So these are the limits of x.
Yes, sir.
Okay. Yes. Are you with me?
Yes, sir.
So
Yes, sir.
let's make it. So however, we are not plotting the function, we're only plotting the domain part. I mean, we are only plotting the region, right? So this is your x and this is your y. So what is your y? Y ranges from 0 to 2, right? So from 0 to 2. So this is your 2. So this is y2, right? And this is your y0. And then your x is 0 and x is 3. So this is your x0, and let's say this is your x3. So that's how it becomes x3. So what is the region now? This is the region? Yes.
Yes, sir.
Yes,
Is it a
sir.
rectangular region?
Yes,
Sir.
Okay, so that's how you know that. So always keep in mind when these limits are constants, so your region will be rectangular region. That's it. Why? Because we'll draw only lines with either parallel to the x-axis or parallel to the y-axis. So of course their intersection will be sort of rectangle. Is it okay? So now,
Yes, sir.
so if let's say if you are getting any problem, then you always write it as, so if you don't want any confusion, this is your dx. So these are the limits of x, and these are the limits of y. So firstly, will you integrate over x or integrate over y? Tell me.
Why?
Why?
Yes. So yeah, y would be easier. Sometimes we can interchange the limits, but sometimes most of the question will not be able to change the limits, right? We'll do as it is. So easily this is dy.
सर अगर स्टार्टिंग लिमिट जीरो ना हो दोनों
क्या चीज? तो भी कोई फर्क नहीं पड़ता, फिर वो लाइंस जो है ना, वो रेक्टेंगल यहां बन जाता। लेट्स से अगर मान लो नॉन जीरो होती, यहां बन जाता कोई रेक्टेंगल। ठीक है,
अगर
मान लो
दोनों
मैं,
सेम ना हो अगर दोनों सेम ना हो स्टार्टिंग
हाँ तो भी रेक्टेंगल ही बनता ना, बस वो कांस्टेंट होनी चाहिए। ठीक है, समझ आ रही है बात? कांस्टेंट होनी चाहिए। ओके, I'll do
Yes,
one
sir.
more question, you will come
Yes,
to
sir.
know that. Okay, so now this becomes what? So let's say this is your 4y minus y cube by 3, and limit is 0 to 2, and next one is x is equal to 0 to x is equal to 3 dx. So we have done one integral. Okay.
Yes, sir.
Yes, sir.
So
sir.
you just put the values over there. That becomes 8 minus 8 by 3 minus 0 dx. Yes. Is this fine?
Yes, sir.
Yes, sir.
Okay. So now x is equal to 0. To 8 minus 8 by 3. So it becomes what? 16 by 3.
Yes, sir. Yes, sir.
X is equal to 0 to x is equal to 3 dx. So this becomes 16 by 3x, 0 to 3. So this becomes 16 by 3, 3 minus 0. So it becomes 16. Yeah, fine.
Yes, sir.
Yes,
Okay,
sir.
it's fine.
Yes, sir.
Okay, so let's do one more question on this. So that is what? Question number 4. And that is pi to 2 pi, 0 to pi, sin x plus cos y dx dy. So now it is dx over here. So you know that these are limits of x, and it is dy over here. So these are limits of y, right? So plotting is not necessity over here. Okay, you can directly calculate it. But let's say if you want to plot it, you want to plot the domain. Okay, so can anybody tell me what is the ranges of x?
0 to pi.
0 to pi.
Yes, 0 to pi. So 0 to, let's say 3.4 something. Okay,
Yes, sir.
3.1. So 0 to 3.1, let's say over here. And what are the ranges of y?
Pi and 2 pi.
Pi and 2 pi. So let's say it is pi over here and it is 2 pi over here. So that means your y starts from pi to 2 pi, and your x starts from 0 to, your x starts from 0 to pi. Okay. So let's draw the lines. Somebody was saying that when it is non-zero, what will happen? So I'm discussing that case. Okay. Yeah. Are you getting this?
Yes, sir.
So this is your line. So see, actually these lines will cross on that side also. I'm not saying that they only start from here, but what happens, your next point is x has to be 0. So that means you will take this boundary as well, right?
Yes, sir.
So you mark your boundaries. What is your boundary? One is x is equal to 0. This one, pi, this one, right? And then, but from here, this is and this is. So what should be your rectangle? So precisely your rectangle would be, let me mark this to this and this and this. Yeah, is it okay? So this is your region. So this is rectangular region. Of course, if it is not non-zero, even then it will become rectangle. The only requirement we have, we should have the constant limits of x and y. Okay, tell me, are you getting this?
Yes, sir.
Yes,
Yes,
sir.
sir.
Now this is your region. So you don't need to plot it. I'm just telling you that how this region can be identified. Okay, so okay, the rule will be the same. We have x limits first, so we'll differentiate. We'll integrate with respect to x only. So this becomes, well, let me take it to the next page. Yes. So now we write it as, so differentiation of sine x is minus cos x, and cos y, we are doing it with respect to x only, to x cos y. 0 to pi. And pi to 2 pi, we are still doing the y. We are left with this. So pi to 2 pi. So you put the limits. Since you have dealt with the x integral, so you'll put limit only for the x variable. So cos pi would be -1 plus pi cos y minus cos 0 plus 0 dy. So what is cos pi?
-1.
Yeah, so this becomes +1 pi cos y. So again, minus minus plus 1. So let me write it as 2. Okay?
Yes, sir.
Yes, sir.
Okay. So now this becomes what? 2y plus pi sine y. Pi to 2 pi. So now, can you do it?
Yes.
Yes, sir.
2 pi
Okay.
answer, sir.
Yes. Fair enough? So now, let's say when you don't have a limit which is constant, then the things are different, right? So how these are given to you. So I'll mark it as double integrals over non-rectangular regions. But always keep in mind that these regions are always bounded to us. Most of the times they are bounded to you, right? Fubini's theorem, we call it as stronger form, right? We'll do only statement. Let f of xy be a continuous function on region R, and R is defined as x lying between a and b and y lying between some function of x, g1x to g2x, right? With G1 and G2 both are continuous on AB, then this integral, that means again the areas, can be written as x is equal to a to x is equal to b, and y is some function of x, g1x to g2x, with again f dy d fxy dy dx. इसी का दूसरा पार्ट कैसा है, इसी को ही y की टर्म में लिखना है, देन आई विल एक्सप्लेन यू दैट हाउ इट वर्क्स. तो यहीं पे फिर हम आज का लेक्चर छोड़ देंगे. ओके, सो व्हाट इज इट सेकंड पार्ट? सेकंड पार्ट इज if R is defined by y lying between C and D and x lying between, let's say, h1x, h1y, just a minute, to h2y, with h1 and h2 are continuous on CD, then again, if you want to calculate that volume, this volume would be y is equal to C to y is equal to D, and x is equal to h1y to x is equal to h2y, f xy dx dy. So let me draw this. तो अब है क्या कि पहले हमारे पास कांस्टेंट लिमिट्स होती थी. नाउ आवर लिमिट्स आर नॉट कांस्टेंट, राइट? तो ये y इक्वल टू सी, y इक्वल टू डी अब कांस्टेंट ना होके क्या होगा, लेट्स से वो किसी तरह का पैराबोला हो जाएगा ऐसा, और इधर से भी कोई पैराबोला अलग शेप से ऐसा. सो नाउ व्हाट इज योर रीजन राइट नाउ? सो योर रीजन इज विल लुक लाइक दिस थिंग. ये ब्लू वाले के ऊपर तुम्हें इंटीग्रल निकालना है. आर यू विद मी? Yes, tell me.
Yes, sir.
Yes, sir.
Okay, so now, can you tell me that along this boundary, x is changing its limit?
No, sir. No, sir.
Yes. And along this, x is changing its limits? Yes, tell
No,
me.
sir.
No,
No, sir.
right? So in those boundaries, x is not changing its limits. But can you tell me that y is changing its limit? Now, see, as x is varying, y is giving you a different values along this path.
Yes,
Yes,
sir.
sir. Yes, sir.
Right. So your y depends upon what? Y is depending upon the value of x.
X.
Yes. So is it fine? Are you with me? So this is not a function. So this is something we call it as and this is your g2x, right?
Yes,
Is
sir.
it true? Is it true?
Yes, sir.
Second case is similar. You have to make it like this, this, this. Now the limits of y are constant from here to, let's say, from here to here. Okay. So this is your y is equal to c and this is your y is equal to d. But this time your x will get varied. Let's say from this to this. So your closed and bounded region will look like this to this to this and to this. Okay. So your x will be a function of y. So this will become h1 of y and this will become h2 of y. Yes. Are you with me?
Yes, sir.
So we'll do the question based on this thing in our next lecture. So that's it for today.